Welcome. We'll just give it a minute here before we jump in, just as people kind of log on there. And then we'll get into today's topic. Right. Welcome everyone. Just at the top of the hour here. So thank you guys all for coming out to today's webinar. Just wanted to mention that today's webinar is recorded and will be posted on YouTube and shared throughout the ecosystem. Feel free to share that webinar recording with your ecosystem as well if you find any particular interesting and valuable insights from the conversation. And without further delay, I will pass it off to Mark Kirby to jump into today's conversation.
Hi, everybody. Well, I'm pleased I'm the one who's not going to have to do hopefully too much work today. Let me just see if I can share my screen to begin with, which is probably the most complicated bit. Let's do that. Is that coming through okay? Can you see that, Nicole? Yep. Okay, perfect. So we're presenting this on behalf of Canada Makes. Just if you didn't know, Canada Makes is we're a not-for-profit promoting adoption of additive manufacturing across Canada and very much involved with networking internationally as well. Clearly the international stage is, let's just say, changing pretty rapidly right now. So if we can go on to the next slide. Yeah. We are part of, just to put this in context, Canada Makes is one of 22 different, at least 22 different clusters across Canada. Some of them are technology clusters like AI for M, which Nicole also runs. And some of them are more market focused, like the Saskatchewan Institute for Minerals, SIMSA, and Marios with the oil sands. So we are part of this connected ecosystem, and today's talks around sustainability. I just wanted to kind of frame it that I think we often hear the word sustainability, and I don't know if sometimes you think, oh gosh, it's another burden, it's another cost, it's another thing I've got to do. I've got to report my CO2 footprint, as opposed to framing it as it is an opportunity and is boldly, I'm going to say, is green the new lean? Is it a way that we do more with less? And again, in our changed global reality, I think for Canada to do more with what we already have is very topical. So having said that, see if I can advance my slide to the next one. The agenda will be, we're going to have, I'm going to call her GI Elissa, Geometric Intelligence. Elissa's going to talk to us about what that is and how it can help with reducing various kinds of waste. I think this is going to be super interesting, and I think this is pretty much a world exclusive for Canada Makes. I didn't know anything about this. If you're going to Hanover Messe, and I know quite a lot of us are with NGen, it'll be launched more on the world stage there, but this is certainly a Canada first. So thank you, Elissa, for kicking us off. In the middle, in our sandwich, is going to be Alexandre, from Polycontrols, is going to talk to us about cold spray, what it is, how it can be used for repair and reuse. And I don't think, hopefully, nobody is going to, as a consumer, it's always a nuisance, isn't it, when our devices don't work anymore and, the right to repair. But this is sort of more on an industrial scale. How do we repair and reuse things using the unique technology of cold spray? And finally, but by no means least, Debjyoti is going to talk to us about how we can get more from bitumen. It's beyond bitumen combustion. I think a super interesting multi-billion-dollar opportunity. So stay tuned for that. And we will have time for questions. I would think each of the presenters will go for around about 10 minutes. And please do put your questions in the chat or use the Q&A. Feel free to give me a hard time. I'm here not as a panelist, but I am involved in additive manufacturing in aerospace. So anything's on the table. And with that, I'm going to stop sharing and try to hand over to Elissa Ross, CEO of Metafold. Thank you very much.
Wonderful. Thanks, Mark. Let me just bring up my slides here. Okay. Hopefully you're seeing that okay. So thank you, Mark, for the kind introduction. I'm not sure about being GI, Elissa. I think we got to work on that a little bit, but for now I'll take it. And thank you, Canada Mix, for the kind introduction to be here, or kind invitation. So yeah, it's my pleasure to be here. I'm really passionate about this topic, about AM and sustainability. I've thought a ton about this. And in general, I am super excited and super optimistic about the potential of additive manufacturing to have a real impact in this space, and in particular to be able to design and produce new kinds of parts that have incredible environmental benefits. However, I have to say that I also believe that vision is still very much in the future. It's a bit of a greenfield vision. And I know this because my company, Metafold, we're a startup based here in Toronto. We're 4 years old, and we've been in this space for that time, and really seen some significant challenges, let's say, around building a business on this promise of additive manufacturing for sustainability and for kind of very innovative designs that have incredible benefits. So while I remain very enthusiastic about this, there are really some significant market challenges, which is in itself extremely interesting. What we did discover in this time is that there's a huge appetite for improving manufacturing in general, and additive manufacturing has a significant role to play in that process, which I'll talk about. We've adapted our technology called geometric intelligence to this challenge, and we help our customers, who are manufacturers, make critical decisions from their 3D data. Put another way, we help them reduce waste in the manufacturing process. And so that's what I want to start off with, is thinking about waste in manufacturing. There's so many ways of looking at waste. There's sort of the triple bottom line approach. There's the 7 or 8 wastes from the Toyota heritage. I wanted to pick out these 4 critical manufacturing wastes that I think we can have a really meaningful impact on. Material waste is, in a lot of ways, the most obvious. There's a certain amount of raw material that simply never makes its way into a final product. But then these other wastes, energy waste, time waste, knowledge waste, whether from failed production runs due to, not accurately vetting the part for the machinery, wasted time in design iteration and revisions, or knowledge waste, which I see as a huge opportunity, really, where these kind of institutional insights are lost in the catalog of previously made parts. It can be very hard to extract insights from those. All of these wastes negatively impact profitability and sustainability. Of course, at Metafold, we think there's a better way, which is this concept of very knowledge-rich manufacturing. Not a new idea, of course. This is something that every manufacturer is working toward. But just to kind of highlight where we see ourselves fitting in, you can think of traditional manufacturing here on the left as these very disparate processes. From design, it kind of gets thrown over the fence to prototyping or validation, and then again thrown over to production. Limited communication between these different groups, and very lengthy rework cycles, redesign cycles with very limited data flow. Of course, this leads to higher waste and lower profit. In contrast, a very knowledge-rich approach, you have an extremely robust data flow between the different stages. And I think the point I really want to highlight here is that much more is done digitally than physically, with the goal being that when you arrive at production, you're in a much more informed place. And this is where I see a really interesting role for additive manufacturing, kind of going back to the classic application of additive as a prototyping method. I see potential still to enhance additive as a prototyping method, not just to kind of get the look and feel of something, but really to create very high fidelity prototyping with all the incredible capabilities we now have in additive manufacturing. So this approach leads to reduced waste, higher profit, and at Metafold, our geometric intelligence API can be adapted to support these data flows between the different parts of manufacturing, all the way from engineering intent down to the machines on the shop floor. So specifically, we support knowledge-rich manufacturing. I like to think of our API as a toolkit for making critical manufacturing decisions. More concretely, some of those decisions might be things like, have I made this part before? A very simple question can be surprisingly hard to answer unless your team has been very good at naming files and keeping track of things. It can be hard to actually find the part if you know you've made it before, but where is it? And so with Metafold, we would be taking a very geometric approach to this, looking specifically for the geometry that matches, not any kind of metadata. The second question here, is additive manufacturing a cost-effective choice? This is super interesting and not straightforward because, as I'm sure we all know, when you're making something with additive manufacturing, the name of the game is redesign or additive. It is not simply make the same part with additive. So typically you're not just comparing the price of traditional versus additive, you're also comparing any kind of performance enhancements and improvements that you get through additive manufacturing. And then my final question here, what is the highest performing shape given a set of manufacturing constraints, whether that is CNC, sheet bending, injection molding, or additive? How do we make the highest performing shape? This is, again, a simple question, hard to answer without a lot of iteration. And this is something that we work on a lot, actually. So going a step further, these are the three main buckets that our API is applied to. So rapid manufacturing analysis, we can extract metrics and information from 3D data that can be applied to costing pipelines, manufacturability analysis. Design optimization is the second one. This is what I was just talking about. How do you find the highest performing shape for a particular application? But you can incorporate all kinds of constraints here from performance, cost, and manufacturing. And then finally, geometric analysis. This is this question of how do you find similar parts? How do you extract institutional insight from your part catalog? And so my last slide here is a case study. I want to bring it all together here as an example project. This is effectively a dashboard that compared conventional versus additively manufactured heat exchangers. And it was for, this is for a client who needs to make this decision on a repeated basis. So they are constantly assessing new specs for heat exchangers. And they have a very, they're really interested in using AM, and they recognize it doesn't always make sense. How do they make this critical decision? It involves a lot of factors. Some of them are based on 3D geometry. And so this is what we tried to do, kind of pulling all together the design, the performance simulation, and the cost as compared to what they have done in the past, what is available off the shelf, and putting it into a format that is accessible to a wide range of team members. And this is important because a lot of these decisions, it's not one person, there's multiple stakeholders. How do you get them all on the same page? And so even having this interface, bringing it all together in one place can help really sharpen the ability to make those critical decisions about how to whether to go with AM versus conventional, and more generally, how to make good manufacturing decisions. So that's a little bit about Metafold and our geometric API. Of course, I'm really excited to hear from my fellow panelists and join the rest of the discussion. So happy to answer questions later. Thanks.
That was awesome. Thanks, Elissa. Really good. And my understanding is, because this is fairly early on, this is an API right now. So people would need to have a conversation with you about how they would actually get to grips with this. I will just break my own rules here. But you talk about, have we ever made a part like this before? And I think the light bulb moment you've had is, we could look for geometry matches versus looking for a file name match or something else like that. And you said it was metadata. Presumably, my simplistic way of looking at something might be I would do an image search on Google to sort of see, has somebody else made something like, what is the state of the art? Are you able to ingest knowledge like that? I had this sort of dichotomy between, you talked about the waste of knowledge potentially within an organization, and yet we've got AI that's threatening to consume all the world's knowledge, isn't it? So how are you addressing sort of at maybe an even bigger level? You talk about heat exchangers and maybe how should we make them? And is there a way that you're able to ingest data from outside an organization?
Of course. Yeah. I mean, our big focus is on translating 3D data into information or insight that can be used in any downstream process. But to be clear, this is not an AI model. This is not something we've trained on an enormous data set of geometry. And in general, that is not kind of that is not happening. Let me just say in that is not happening in AI right now. So our approach is very focused on using a given organization's internal data, but certainly this can be compared against any other data set, or you can run any any data through it. And so we have our own kind of proprietary data set that we have amassed, but this is not based on that data set, if that makes sense.
And one last question. In terms of price performance, I guess one of the issues we often have with additive manufacturing is the upfront cost may be higher, but the lifetime benefit, we will argue, it may offset that. How and you said you've been 4 years on this journey with Metafold, and it's not been a completely smooth road. How have you found that sort of the sticker shock of a high performance solution that has lifetime advantages? How does that discussion go, Elissa, in the companies that you've worked with?
Yeah, I mean, exactly as you say, it can be challenging to appreciate that. I think that has been a big obstacle, but where we continue to see interest from this is in the parts of aerospace where removing materials really matters. And there's this very clear connection between the weight of a part and how much they can, what price tag they can put on that part. So I still see a lot of potential there, but I think, on the costing dashboard concept, it is really important to try to paint a longer view. And this is, I think, part of the struggle right now. It can be very difficult to paint that picture. But we're trying to bring in that longer view so that people have more visibility into the true cost of these parts.
Well, certainly, it's an ever-changing view, isn't it? And we wake up today, and today is a little bit different from yesterday. So, thank you so much for that, Elissa. Without further ado, I'd like to hand over to Alexandre from Polycontrols to talk to us about cold spray and repair and reuse. Thanks, Alexandre. I think you might be muted right now, Alexandre.
Appears to be frozen as well.
I was just gonna suggest the same.
Maybe switch the order.
Okay, Alexandre, can you hear us? Can you nod if you can hear us? No. Okay. Let's move that. We will switch it up then. I said it's an ever-changing world, so we'll go to Debjyoti Zen from Red Deer Polytechnic, and this is gonna be a team effort where I'm gonna try and play the slides and you're gonna tell me when to move on. So let me just share the screen. Take it away, Debjyoti.
Thanks, Mark, and thanks to all my fellow panelists, and thanks for inviting me to represent Red Deer Polytechnic in this great event. I hope you can all hear me clearly.
Yep.
Perfect. So today I'll be presenting a multi-billion-dollar opportunity, not only for Alberta, for Canada and rest of the world. So this is having more from less, as Mark pointed out in the beginning. So I'll be talking about bitumen beyond combustion today and how we can unlock high value materials through additive manufacturing and few other advanced manufacturing process. So I am Debjyoti Sen. I am the director for Centers for Manufacturing and Energy Innovation at Red Deer Polytechnic. And before I jump into bitumen beyond combustion, I'd like to talk about what we do at the Polytechnic in terms of applied research and what my center does. That will give a little bit better perspective about what we do and how it relates to the topic I will be talking about. So Red Deer Polytechnic's applied research is a growing applied research department, and we are #1 in terms of annual growth in research funding in 2022. We have been consistently in the top 50 research colleges in Canada. We do around 70 projects in a year, and we partner with 190 companies. So in applied research, all the projects we do, it's aimed at solving an industry problem. So it's very applied. Industry comes to us with their problem statement, and we try to help the industry in solving those problems based on the resources and the infrastructure that we have. So there are 4 pillars in applied research. One is the manufacturing innovation. One is the energy innovation. Then we have healthcare innovation, which recently started. And then there is social innovation. And there is one common framework which connects all this department, that is data-driven innovation. So as of today's day, we focus a lot on data because a good data tells you in an unbiased way what the future looks like and what the present looks like. So that's a common platform we have among all the departments. So I'll talk a little bit about our Centers for Innovation in Manufacturing. So it started in 2009, and we are one of the leaders in when it comes to 3D printing and additive manufacturing. And we hosted Alberta's first commercial 3D printer in our center. We have completed so far around 400 industrial projects, and we engage with hundreds of industry on an annual basis to understand the industry need in terms of what are the problems they are trying to solve, how the future looks for those industry, and then we try to use our infrastructure and resources to solve those problems. Most of the industry we work are small and medium size industries who wants to develop a product or optimize their product. They come to us and use our infrastructure and resources. We walk them through and bring their ideas to life. So we got the Technology Access Center designation in 2020. So that's federally recognized by NSERC. And that gives us the ability and the funding to grow. So we started growing in 2020. We have presently 15,000 square feet of industrial accessible space, and we are expanding with a new building, which will be completed sometime next year, and that will have additional space, and that will host automation, injection molding, and data-driven innovation. So we have around $8 million of manufacturing equipment. We have an in-house team of engineers and we work with cross-discipline across our campus. We have a permit to practice from APEGA, and we are also a member of Additive Manufacturing Network. So that's about us and the department. Now I'll jump into bitumen beyond combustion. So this is a multi-billion-dollar opportunity, as I said, and Alberta is well positioned for this amazing opportunity. So what you see here is the economic potential of bitumen. So as you can see in the picture, there are two ways that we can split the idea. One is the light, and the other one is the heavy, coming from a barrel of bitumen. So the light one is typically used for fuel. So if we value that at $30 per barrel, and then we separate the heavy part from it, then the heavy part can be used in carbon fiber, which is valued at $179 per barrel. Then there could be asphalt binder, which is valued at $50. Then there is activated carbon, which is valued at $100. All of this product has tons of industrial and commercial use, which I'll go in a later slide. But one of the purpose for this slide is to show that if we think in this way, then it's feasible and possible to extract more value from a barrel of bitumen. So let's absorb that thought and see what is the broader economic impact. So the broader economic impact will be an additional $33 billion in revenue if we assume 1 million barrels per day are converted into this kind of product. So, and also it will create thousands of new high-tech jobs in manufacturing, material science, and can stimulate the economy overall. And the processes I'll be discussing can be more sustainable, since we are not upgrading the heavy part of the oil and converting them into other materials, so it will be inherently more sustainable. So some of the key products we discussed and how we can have 1 barrel of bitumen to produce more dollar per barrel. Now we'll move to the next slide. So the next slide will be talking about some of the processes that we can use and some of the gaps in the process. So the feasibility of the overall process and the economics looks good, but we have to bridge the technical or the technological gaps to make it happen. And Red Deer Polytechnic is closely working with Alberta Innovates, and Alberta Innovates have done a good study on this topic. They have a white paper, which I recommend everyone to read. The link is there on the previous slide. So what we are trying to do is using additive manufacturing to find out how we can make tangible products out of the heavy crude. So one of the questions that comes is why additive manufacturing? Because additive manufacturing has less waste, so it becomes more sustainable. And with additive manufacturing, you have more freedom to make different composite. So you can optimally mix carbon fiber and make composite, which are inherently stronger, lighter, and more sustainable. So that's the carbon fiber composite. Now there are other products like graphene and carbon nanotubes. These are used heavily in electronics for high performance. And then there is the sustainable asphalt and infrastructure material, which can be proven to extend the life of roads and construction. So I'll move to the next slide. So what are some of the applications of the products that can be made from bitumen beyond combustion materials? So some of the sectors are automotive and aerospace. So carbon fiber composite reduce vehicle and aircraft weight and improves fuel efficiency and lower emission. So an estimate shows that up to 22 to 36% emission can be lowered if we reduce the weight using this type of material. And so that makes aircrafts more fuel efficient, and there is a lot of space exploration going on now. So with that, every gram matters when it comes to space travel. So that could be one of the area where these materials can be used. And then there is energy storage and electronics. So with all the electrification that is happening in the world, that field is really exploding. And so graphene enhanced battery is one of the things that is responsible for fast charging and gives longer lifespan to batteries. So that's something that can be looked into. And then there is the supercapacitor from activated carbon that improve the renewable energy storage and grid efficiency. Then there are 3D printed conductive material which can provide the next generation electronics. For example, embedded graphene in textile and other material which helps you make flexible electronics. Then there is construction and infrastructure. That's another sector. So 3D printed carbon fiber reinforced concrete is one area. Which is stronger, crack resistance, buildings and bridges can be made out of that. Advanced asphalt binder that gives you long lasting roads and reduce maintenance cost. Prefabricated 3D printed structure, which is gaining a lot of attention today. So you can have big factories where you can prefab a lot of structure, which makes product faster, construction faster. So that helps more for sustainable construction. So that's in a nutshell about the opportunity. And I'd like to quickly thank all our funders, which include Periscan, Alberta Innovates, NRC, and all other provincial and federal funders, all our clients. With their support, we buy a lot of equipment, we help maintain them, and also we hire a lot of talent pool, including students. And thanks to Canada MEC team for giving me this opportunity. Thank you.
Thanks very much, Debjyoti. As you say, a multi-billion-dollar opportunity, but with more than a few technical problems to turn it into a reality. Let's, just in the interest of time, we'll continue on. We'll repair the connection, hopefully, to Alexandre, and reuse it. See if you can share your slides and tell us about cold spray and repair and reuse. Alexandre, over to you.
Yeah, thank you, Mark. Let's hope this goes better now. Okay. Do we all see the presentation?
Yeah, that's
okay,
perfect.
Excellent.
That's good.
Thank you. So thanks for the opportunity for talking on behalf of Polycontrols today. I'm going to try to talk to you about cold spray and how it can contribute to a sustainable future. So Polycontrols, it's a company that's been founded in 1982, so we have over 40 years of experience. We have 2 facilities located in the South Shore of Montreal. We have over 40 employees, a multidisciplinary team working with different technologies, and we value our strong collaborative network with industries, with the academia and the NRC and other research centers. And I'll talk about 2 activities of Polycontrols today. We have a strong experience in instrumentation for flow measurement and control. So we design and manufacture custom gas panels for regulation, pressure regulators, gas distributions, etc., for a variety of industries, including metallurgical, petrochemical. and we deliver these systems. As I said, in-house, we produce them, and so we can establish a direct support with the clients that we serve. And we can also we can also cert and calibrate these devices as we have the highest standard accreditations that are available for this kind of businesses. The other business activity that we devote to is metal additive manufacturing. So we focus on repair, manufacturing, and revalorization services for parts. We also do integration of sensors. So you can think of anything from distance sensors, thermocouples, um, infrared cameras, all that. We can integrate that into tailor-made softwares for industrial cells. And we also have experience delivering turnkey solutions for thermal spray and welding facilities. So I've been talking about cold spray, and I think it's going to be beneficial for everybody if I talk a bit about what cold spray is. So basically, we pressurize and heat an inert gas. We work only with nitrogen, so that's a good starting point. It's available in cheap gas to obtain. We pressurize that into a chamber. Then the gas is passed through a specific kind of nozzle that allows this gas to achieve supersonic velocities. Then we add particles to that gas stream, and these particles are accelerated and heated. And when they impact into a substrate, the that energy, that kinetic energy is transformed into thermal and plastic deformation energies that creates a bonding that works like cold welding. There's no fusion involved. And as fascinating as this process is, it allows you to do a lot of things, but the key advantages, in my opinion, are that it has no fusion. So there's very, very low heat input compared to more traditional additive manufacturing and other repair processes. There's no need for atmospheric control. So you can do that in a large room or a small room, but you could use it, but it's a rare need. I mean, you could use control of atmosphere. There's almost unlimited size restrictions, so you can work on small parts or very large parts as long as your robot can reach and place the cold spray gun where it needs to be. You can spray there. You can work with a multitude of materials. So we were talking about rare materials, critical minerals. So you can think of traditional metals. You can also think about tungsten, tantalum, silver, you name, like as long as it's metal, usually cold spray can do it. And you can deposit these metals at a high deposition rates, anything that can be between 0.5 to 7 kilograms per hour. And because of these key advantages, the main application or the main cases for cold spray lies in repairing expensive parts that have strict dimensional tolerance and high sensitivity to heat, which you probably can imagine. That means aerospace components, and they have each of them cost tens of thousands of dollars to remanufacture from scratch. So you have a lot of problems with that with supply chain. So repairing these components are obvious. There's an obvious business case for that. There's an obvious financial sustainability case, and also material savings standpoint. It's very advantageous. So if I go to the next slide. So to summarize what cold spray can do for a sustainable future, I see two main things. Like first is the life extension of course. So repair and manufacturing is the bread and butter of cold spray. We can reduce material consumption because we're not preparing a new part. We can also apply the material exactly where it's needed without distortions, instead of placing the whole part into a furnace or a chemical bath. We can do that material application where it's needed. And we can also extend the life of these parts by creating improvements such as improving corrosion or wear resistances. Another less known application for cold spray is improvement of production and process design. So we can add functionalities, and this needs to go into the minds of the designers. So we can, for example, increase the conductivity of certain elements by adding, copper, by adding other high conductivity elements, or we can even put, for example, permanent magnets into a part. So in the context of electrification, this is an interesting approach. Cold spray can deliver some interesting results. So that summarizes what I had to talk about cold spray. And then I'm happy to take questions if there are any.
Thanks, Alexander. So I was just making a note there. So Elissa can give us geometric intelligence, but you can give us you can embed new material properties as well with cold spray. That's pretty. So the combination of geometry and new material properties. Well, first of all, thanks everybody for giving us a little window into what's going on in Canada in these different areas. Super interesting, I think. I have asked the audience if they have any questions. Nobody's put anything in the chat at this stage. So I don't know. I've been the one asking all the questions. I don't know if anybody wants to ask me a question in terms of aerospace and additive.
I would take you up on that. I'd love to hear more, Mark, about what's going on in aerospace with respect to additive.
Sure. Thanks, Elissa. Good to be in the firing line. So Tronos is we're here in PEI. We're involved in a project. It's with Airbus. It's with General Electric. Make sure I get all the names. It's like the Oscars ceremony here, isn't it? CREAC, Alexandre, CMQ, University of Laval, Polytechnique Montreal. Looking at reusing titanium in particular for aircraft, it's obviously a widely used material. And we're looking at everything from, can we just take the fuselage of an airplane and, that has big lumps of solid titanium. What are we going to do with that? Can we just reuse the fuselage and turn it into potentially powder for additive manufacturing? And can we even look at, say, chips from machining? We talk about a lot of the waste. Can we look there? Or can we look about reprocessing powder? It's interesting, Elissa, you talked about the pain that you've been through in I know it's been more than 4 years, but it's just the 4 years you can remember. But when I started in additive about 10 years ago, the idea of reusing powder at all was a big no-no. It was like, oh no, you can't do that. And of course, we've fairly quickly realized that if you don't reuse powder, then you will not have a business case. And it is always a Jerry Maguire, show me the money. So we have to reuse powder. But now we're talking about, can we use used powder? Can we recycle it? So, and it's a research question right now. So that's a project that we're involved in. We qualified a part to fly with the FAA. Using powder from APNC, GE. So we kind of have some pretty interesting baseline data to compare sort of these novel new powders to. So that would be Tronos's role in that. And obviously we would hope that we would have a seat at the table with companies like Airbus looking at, I hope they're going to use your API, Elissa. And again, it's a lot about networking and what we can do, and the people on the call who are listening in, it's very much about how do we talk to each other. As Canadians, we're pretty good at collaborating, I think, and we do have, despite everything, a lot of trust. So I would just encourage people. Hopefully, there's maybe some inspirations here. Aerospace is still tough. It's slow going. You talked to Elissa about the dollars per kilogram that can be saved and how we translate that. And I admitted in my youth that I used to champion this a lot and ask people, how many dollars per kilogram is it for an aerospace part or a satellite part or a car part? And the answers were it's $10 a kilogram for an automotive part, 100 for aerospace, and 1,000 for space. I think one of the things that is true with space, and Debjyoti, said this, is you kind of get paid up front. If your system weighs less, then you pay less for the launch, and you can do more with your payload, with your product. In aircraft, the payback is over the lifetime of the system. And it may be as critical as you get selected as a supplier. Your undercarriage is lighter than somebody else's and performs as well. And therefore you have a 30, 40-year contract. The airlines are the ones that sort of save the money. So following the money can be tough. But yeah, that's what we're doing here in aerospace, and we're off next week to Washington. There's a satellite show there, and we've certainly seen the appetite for risk is a little bit different in unmanned systems, shall we say, than with aircraft. So again, sometimes it's about how do we go faster, and I'd encourage everybody to kind of have a portfolio. You want some risky. You want some speedboat projects along with some oil tanker projects powered by the was it the light fraction or the heavy fraction? I can't remember, Debjyoti, that goes into fuel. I think it was probably the light fraction that goes maybe into some ships. And it's interesting, we've got a ship that just sailed from the UK it's called GT Wings. It's sort of a very high tech. It isn't a sail, but it is a sail. How we're looking at technology to provide new solutions, better solutions. And I'm very optimistic for Canada. We have some great technologies. We've seen some of them here today. We have others. Mosaic Manufacturing is one who are doing some great things in terms of the potential for distributed manufacturing, so we don't have to have transportation costs. And we're going to need software to tie it all together for sure. And companies like Polyunity are doing this in healthcare. So I think, I'm optimistic. Sorry, you asked me the time, and I told you how to build a watch there, Elissa. Sorry, but that's what's going on there. So,
yeah, that's awesome. It's super interesting. Another thread I wanted to pick up on, actually, I think Debjyoti, you mentioned AI and that you had some thoughts on this. I would love to hear you expand on that.
Absolutely. So everybody is talking about AI these days, especially with the advent of ChatGPT. But AI had been around for a very long time. So what's new and what is happening in the two worlds in manufacturing and material science is quite interesting. So what AI is doing with the high-end processors and the GPU power, we can fast track all the experimentations that we have done in the past. So for example, someone cuts a piece of metal, sees for the first time under a microscope, gets the structure, write it down, make an hypothesis. So all this process, when get digitized and scaled, that 100 years of humanity's effort can be done in a couple of days now, right? So that's how fast we can do things to create new materials. And there are a lot of open source platforms which have been launched. IBM has launched one, then Google has one, which uses different AI tools where you can give criteria and it can create new materials for you. So I think that field will keep growing. So the limitation that we'll have is actually to fast track those experiments once the materials get created in theory. Like how can we get the physical piece of the material? So that's where robotics and automation comes in to fill in that gap. So I was there yesterday in a robotics meetup in GTA area. So they were talking about what is the new development in robotics. That was also very interesting because AI is playing a major role. So industrial robots have been around for a very, very long time. So the innovation is not happening in how the robots get more efficient? Yes, there is some, like how can you have more efficient motors and stuff like that, more accurate. But the major innovation is happening around the sensors around the robot and how the robot can process more data to make certain decision. So now the part is what decisions are important, like can AI make critical decisions in certain way, like doing that critical thinking part. So today, I think the problem statement is if you break that critical thinking into smaller chunks of modules, then AI can do it and can assist you and fast track your way of thinking. So yeah, in terms of material science, new materials development, and in robotics, I think there is a lot of interest and there will be a lot of growth if we combine the hardware and the AI part.
Awesome. That's, as you say, it's the Internet of Things, isn't it? How we can have all of these sensors, more and more data. How do we make decisions? How do we need 5G to help us with all of this in some of our remote communities? We've got companies like Cobionics who are doing telemedicine with telerobotics with ultrasound. I think we're probably not going to see open heart surgery by robots anytime soon. That's not the low-hanging fruit. And again, we're smiling, but it's sometimes, people want to go and build a GE fuel nozzle, and that's not maybe the best place to start. And sometimes starting in polymers makes a lot of sense. There was a question from Martin on where is the hotbed of know-how about additive and how do we help down select? I think Canada Makes is, that's kind of what we're here for. That's what we're here as a network for. We're not promoting any one particular technology. In fact, we're not even promoting the technology. Those of you who know me well will know that my answer is always, and here I go. This is probably not going to be in focus here, but this is, if you can machine it from solid, machine it from solid. My camera's not going to focus on it, but there we go. That's a spacecraft bracket that's been machined from solid. And there's always an alternative, and Elissa was talking about this with her API. We're always comparing. We make better decisions as humans with A versus B. Do we want to save the dolphins from being caught in fishing nets? Should we give $1 to that, or do we want to give $1 to stopping farm workers getting cancer? And when you're faced with, and I plagiarized that from Thinking Fast and Slow, those of you who've read it, but we're always going to make better decisions when we have an A versus B. And I think that technology down select is exactly the same. And it's not just about what's the best additive technology. It's about, as Elissa boldly stated, to boldly go where no man has gone before. What is the best way to make something? What's the best shape? What's the, how do we improve manufacturing in general? So, I think it's a very exciting time for us with all of these technologies, with software, with some fantastic people who we've had on the panel today. I just want to thank everybody for being here. I think we'll probably wrap it up there. On a high positive note. It's good. We need some positives these days, don't we? Thank you very much, Nicole, for hosting us as always. And if you want to reach out to anybody, Nicole at CanadaMakes. It is .ca, isn't it?
Yeah.
.ca, get it right. Or the website. And obviously we've got Elissa at Metafold, metafold.com, Debjyoti at rdpolytech.ca, and Alexandre at Polycontrols. You're in Montreal, aren't you, Alexandre? Is that where you guys?
Yes.
Yeah, yes, right.
Exactly.
Yeah. Thanks everybody very much. Thank you to NGen for hosting this. Nicole, do you have any?
I was just going to say, just to echo Mark's point, I'll be passing around, links and websites and contact information. If you guys have any other questions for a specific panelist or for the group, feel free to reach out via the email I reach out to you with the recording, or any other platform you feel comfortable. With that, we can wrap it up. Thank you guys all so much for joining the panel today. It was a great conversation.
Thanks, everyone.
Thank
Bye-bye.
you.
Thanks, everyone.
Thank you.